So n, you can, again, shortcut, look at the row of the periodic table that your element is in, and that'll tell you your n. Now the next quantum number is L. L can be anything up to n minus 1. That means when n is 1, the biggest number that we can get for quantum number L is a 0. And then it goes up from there. It can be 0, 1, 2, 3. So let me give you an example. Let's take all the possible values for L when n equals 1. Well, when n equals 1, L can only be 0, only up to 1 minus, or this number minus 1. Let's say that n equals 2. Well, it can be everything up to this number minus 1. So that means L can be 0 and can be number 1. N equals 3. We can have everything up to this number minus 1. So that means L can be 0, 1, or 2. So again, once you know what your N is, you can figure out what your L's are. Alright, L is important because it tells us the shape of the orbital. So knowing the number of L tells you whether or not you're going to have a spherical or a 1s, 2s, 3s type orbital. If L equals 1, we get a p. This is where you have your 2p, 3p, 4p orbitals. When L is 2, we have the d. This is where the d comes from in our electron configurations. This is the d subshell. And L can also be 3, which corresponds to our F subshell. Now, the possible values of the next quantum number is ml. And this has values of everything from negative L all the way to positive L. So this can be negative L all the way through 0 to positive L. And this really tells you how many orbitals there are of this type. So let's take an example. Let's say that n equals 1. Alright, well we know that L has to be 0. Alright, well when L is 0, ml is automatically 0. And so that means the only type of orbital we get is the s. Let's take a different scenario. Let's say n equals 2. Okay, what are the values of L? Well, L can be 0, which would make ml 0, which would mean we get an s shell. But L can also be 1. And if L is 1, that means ml can be negative 1, 0, or positive 1. That gives us 3 different equivalent p shells. And so this is where we start getting something called degenerate orbitals. And what you end up learning is that every one of these degenerate orbitals, whether it's an s, a p, a d, they can all hold 2 electrons. So an s shell can hold 2. The p shell, since there's 3 of them, and they each hold 2, can hold 6 total electrons. And this corresponds with the periodic table. I'll show you a picture right here. As you can see, there's an s block, a d block, a p block, and an f block. And if you look, the p block actually has 6 positions. 6 electrons will fit in there, and that corresponds to the 3 shells and the fact that they hold 2. Look at the d block. There's 10 electrons that fit in there. That corresponds to having an n equal to 3, and ml, sorry, let's say what L is first. L would be everything up to 3, which could include 0, it could include 1, but when it includes 2, then ml is -2, -1, 0, 1, and 2. And we end up getting 5 orbitals, 5 subshells, I should say, that are all the same energy. And there's the d shell, right? L2 is the d shell. 5 orbitals, they all hold 2 electrons, that's 10. And if you can imagine, the f shell is going to give us 7 orbitals, and 7 times 2 is 14. take a look at the periodic table, the 14 electrons that correspond with the F shells, or the F block. So the way that we determine quantum numbers can be from the periodic table. You can look at the periodic table, find your element, let's say we're looking at nitrogen. You can look at the row it's in, that gives you N. Look at the block that it's in, S, P, D, or F. That will tell you your quantum number for L. Then we can determine ML through something called the Aufbau principle, and we'll go over that in another video.